So in this video, we're going to talk about the differences between distance, displacement, speed, and velocity. Four major terms that we're going to use throughout the course of the year for physics, because they do have a difference between them, and it's going to matter in terms of things that how we approach different problems. So if we take a look at this first relationship, distance versus displacement. So distance is basically how far an object travels without taking direction into any account. So if this person goes on a little loop around this oval right here, say it's a track, that would mean that they would have gone maybe about 400 meters along that loop. That's how far they would have traveled. However, when we take a look at the concept of displacement, displacement is a little bit different. Displacement is about how much an object changes their position by during a movement. Okay, not how far they go. What matters here is how much did their position actually change from when they started to when they finished. And we're always going to find that by taking the difference between a final point where they are at and initial point where they finish. And if we look at that person who did that loop, well, they started and finished at the exact same spot. So in this case, even though they walked a distance of 400 meters or ran or whatever they did, they really displaced themselves by nothing. Because if you took a picture before they started racing and after they were done, they're back in the same spot. Along those same lines, dealing with speed and velocity. Speed is the rate of movement regardless of direction. So, for instance, if we talk about this person again here, they go around the loop. Say they go that 400 meter distance. Okay. And let's say they do it in 40 seconds. So that means, on average, regardless of what direction they were going at a speed, which is distance over time, of 10 meters per second. Okay, that's on average of how fast they were moving, because it doesn't care if they're going around in a circle. However, if we go to velocity, this is where it's not just the rate of movement, but it's also the direction of that movement matters. So initially they might have been moving like this, but when they got to the bottom, they were moving in this direction. Over here, they're moving this way. Over here, they're moving this way. Thing is, they end up back where they started because all those movements in one direction are completely canceled out by the movements in the other direction, so they end up right back where they started. So because of all that shifting of direction, our velocity is going to be, it's called our displacement, our delta x, how much we changed our position by, divided by how much did time change, how much time did it take to do that. And because they started and finished in the same spot, well, their delta x is 0 meters. They didn't change their position over the course of the entire motion. They ended up right back where they started. And even if it took them 40 seconds to do it or 10 seconds, it doesn't matter, because on average, their velocity is 0 meters per second because they started and finished at the exact same point. So if we take a look at this graph here as an example, we solve for a couple different things here. We might solve for the displacement from 0 to 6 seconds. So that's delta x equals xf minus xi. Final position at 6 seconds. They are at 7 meters. Their initial position when the whole thing started was 2 meters. So their displacement for the entire motion would have been 5 meters. The distance they traveled is how far did they actually go. So if we look at the first part, they started at 2 meters, they went to 9 meters, so that's 7 meters over that first section. Then they went from 9 back to 7, so to get from 9 to 7, that's going to be 2 meters. And then they went from 7 down to 2, so 7 to 2 is going to be 5 more meters that they traveled. And then they went from 2 to 4, so that's an additional 2 meters. So all of those, regardless of direction, are positive numbers, are going to add together. So we get 7 plus 2 is 9, plus 5 is 14, plus 2 means they went a total of 16 meters for the entire motion. Okay. If we look at their velocity for all 10 seconds, well, velocity is the displacement over the time. If we look at the displacement for the entire thing, they finished at 4 meters. They started at the 2 meter mark. It took them 10 seconds to do it. So their velocity on average for the entire motion would be 0.2 meters per second. Their velocity for the first 4 seconds, well, again, velocity is delta x over t. They finished at 9 meters. They started at 2 meters, and it took them 4 seconds to do it. So 9 minus 2 is 7, divided by 4 is 1.75 meters per second. That was our average velocity for that. The last one is speed for the entire 10 seconds. Well, speed is distance over time. The distance for the entire motion, we already said, was 16 meters. Took them 10 seconds to do it. So on average, they were going 1.6 meters per second. Okay, so hopefully this all makes sense. You understand the difference between distance and displacement. Again, displacement has direction, distance does not. Velocity has direction, speed does not. So velocities can cancel each other out if they're positive and negative. Speed, every single speed is positive. They're all added together because it's just, are you in motion or not? Velocity is, are you in motion and do you have a direction? Displacement is, did you change your position and how much did you change it by over the time period you're looking at? Whereas distance is, what route did you take to get there? How far did you actually go in the process? So if it all makes sense, and now you have one more problem that you will try all by yourself. I'll have a couple questions here for you to answer.